and I'm very glad to present our work in EUROSYS 25. This is the joint work with the Alibaba Cloud. So in this work, we focus on the cloud block storage, a fundamental storage service in public cloud. So at Alibaba, our EBS system adopts a three-tier disaggregated architecture, so which is also widely adopted by other cloud providers like Azure and Google. The first tier of the EBS is the compute node, which serves user VMs and their virtual disks, that is VDs. And the second tier is called the block server. The block server is responsible for EBS-specific logic such as three-way replicas, erasure coding, snapshots, and more. And finally, the third tier is the trunk server, which is essentially a distributed file system for data persistence. So in the EBS, when a virtual disk issues an I/O request, it first goes to the block server. And then the block server generates 3 replicas of the data and sends them to the corresponding trunk server. So along this EBS I/O path, we have deployed layers of load balancing and caching to handle the skewed user traffic. So in the guest OS, we have the native page cache. And in the hypervisor, we deploy a load balancer and a rate limiter to manage the VD traffic. And in the block server, we design a prefetch cache for the read traffic, as well as an interblock server load balancer. But even with these mechanisms, we still run into some unexpected hotspots. In this work, we aim to dive into how these hotspots emerge and what we learn in fixing them. So in fact, traffic skewness is not a new thing, and there have been many field studies on this topic. However, this work has limitations in these 3 dimensions: a scale, workload, and scope. For the scale, existing work collects data on hundreds of VMs and thousands of VDs. But this scale is still too small for a production system with millions of VMs. And for workload, this work only covers a few types of VM applications, whereas public cloud runs extremely rich applications. And for scope, they either focus only on the compute nodes or the storage nodes and lacks a holistic view of the disaggregated architecture. Hence, in this work, we want to study the traffic skewness in a mass production EBS system. So in our study, scales up to 60,000 VMs and 140,000 VDs. To the best of our knowledge, this is the largest deployment study so far. So what's more, our data covers over 30 different types of VM applications, and this work also takes a global view at the disaggregated stack. So next, we will introduce our collected dataset. So our dataset consists of 3 parts: the I/O trace, traffic summaries, and user specifications. The I/O trace is a downsampled record of the VD I/O. It includes basic I/O information like OP code, I/O size, and LB offset. It also captures the EBS components that I/O passed through, along with the corresponding delay. And the traffic summary aggregates the I/O trace to the throughput and IOPS, but at full scale without any downsampling. And the user specification records user ID and the configuration of their VMs and VDs. For example, how many VDs a user purchased and their capacities. So we will begin our findings in the aspect of load balancing. So first, we look into the load balancing inside the hypervisor. So on the compute node, each VD can be seen as an NVMe device with multiple queue pairs. And to balance the workload of different, and in the hypervisor, there are multiple worker threads running to handle the I/O traffic coming from these QPs. So to balance the workload of different workers, one-to-one round-robin binding is used between the QPs and the workers. So the first question is, how does the balancer work? To quantify the workload skewness of different workers, we use the concept of coefficient of variation. The COV ranges from 0 to 1, with higher values indicating more skewed workloads. So our data shows that the median COV of the sampled compute nodes reaches 0.7 for write traffic and 0.5 for read traffic. These are actually quite extreme values. For example, when the COV is just 0.2, the hottest worker already handles 2.6 times the traffic of the coldest one. So in the word, the round-robin balancer works poorly in the production. So next, we break down the traffic inside the VM to understand why the balancer doesn't work. So first, we look at the VM to VD traffic. We also use the COV to measure the traffic skewness, and the result shows a significant VM to VD skewness. But this makes sense. Within VM, traffic typically goes to a data disk rather than the system disk. And similarly, we analyze VD to QP traffic. Surprisingly, we find that the traffic within a VD is heavily concentrated on just a few QPs. Digging deeper, we find the root cause. The default scheduling policy of the block MQ is none, and this means that unless the user explicitly configure it, the L traffic will only be handled by a single QP of the NVMe. So we wonder if there is any existing work can address this issue. We noticed that prior works proposed the periodic QP to WT rebinding. This method periodically identifies the hottest worker and swap its QPs with the coldest one. So we evaluate the periodic rebinding on our hypervisor using a trace-based simulation. So in the figure on the left, each point represents a compute node. The x-axis shows the normalized rebound frequency, while the y-axis shows the rebound gain. The gain is defined as the ratio of the COV with rebound to the COV without rebound. The closer the gain to 0, the more balanced the workload after rebound. So in the figure, we found that some nodes achieve significant gain even with a low rebound frequency, as highlighted by the right circle. So however, for other nodes, as indicated in the blue, even with a high rebound frequency, the imbalance remains unsolved. So we further examine the traffic patterns of the hottest worker in both types of nodes. We find that the nodes in the right circle can benefit more from the rebound because their traffic is relatively stable. And in contrast, the nodes in the blue circle experience highly bursty traffic, which makes the rebound less effective. So in other words, for the blue nodes, we have to increase the rebound frequency even further to make the traffic imbalanced. But doing so would introduce an unacceptable overhead, since the I/O should be stopped during the rebounding. So what is a more promising solution? So to answer this, we should first understand the root cause of this issue. This issue comes from the 1QP to 1WT binding. This design is to achieve a lock-free execution on the workers. For ultra-low latency, we do not want multiple workers to access the same QP. However, this design inevitably introduces hotspots because once a QP becomes hot, its associated worker becomes hot as well. So a better solution is to allow multiple workers to serve the same QP concurrently. That is 1-to-n binding. However, this cannot be efficiently achieved in software. We experiment with techniques like work stealing and lock-free queues, but they can introduce significant processing latency. So a more effective approach is to use a hardware-based dispatcher, for example, the AXI stream on FPGAs. So we have another paper that takes a deeper dive into this topic. So next, we look at another mechanisms in the hypervisor, that is the throttling. So as we discussed earlier, the traffic inside a VM can be skewed towards certain VDs. So let's see a real-world case. In this example, a user VM had 32 VDs mounted, and one of them is experiencing a burst. So when the traffic hits the throughput cap, throttling is triggered, and the VD starts to suffer from long tail. At the same time, we look at the VM's total storage traffic, shown at the blue curve. And we also plot the total throughput cap of all the mounted VDs. That is a blue horizontal line. So we can see that there is still some headroom below the VM's total cap. In other words, the other VDs still have capacity to let more traffic pass. So we propose a simple capacity lending mechanisms across VDs to mitigate the throttling. So as shown in the figure, each VD of the VM has its own traffic cap. Suppose one of them, say VD2, is bursting and throttled. So at this point, we allow the VD2 to temporarily borrow and use the capacity from other VDs that are not being throttled. So this helps VD2 escape from the throttling. So we want to know how that these simple mechanisms work, hence we perform a simulation on the collected data. During the simulation, we periodically detect the throttle VDs and allow it to borrow capacity from other non-throttled VDs. The amount of borrowed capacity is controlled by a parameter called the learning rate. So to quantify the benefit of learning, we define a metric called learning gain. In the formula, the TWO represents the total duration that the VD experiences throttling without learning, and the TW represents the total duration with learning. So the gain ranges from -1 to 1, and a larger value indicates that the throttle duration is reduced by learning. This figure shows the CDF of the learning gain under different learning rates. So from the results, we find that for a small portion of samples, throttling duration even increases with the learning mechanisms. In other words, the learning can sometimes backfire. So upon further analysis, we found that the current learning design may cause the VD that learns capacity out, for example, the VD3, to be throttled again if there is a sudden burst. So therefore, to make the learning mechanism more effective, we have to predict the VD traffic accurately. So next, we will discuss the cache across the EBS L stack. So as talked earlier, along the EBS L path from the guest OS to the block server, there are two layers of caching. So for example, the page cache inside the guest OS and the read cache at the block server that prefetch data from the persistence layer. So however, our analysis shows that this mechanism does work, but not so well. So the first question is, what is the access pattern on the LBA? So to answer this, we divide each VD's LBA into fixed size blocks and identify the most frequently accessed ones, that is the hottest block. In the figure on the right, we plot the access rate of the hottest block of all the sampled VDs and their different block size. So the results show that just 3% of the LBA can contribute to 18% of the total traffic in terms of the median. So this indicates that even with the page cache in the guest OS, there are still clear hot spots on the LBA level. So we want to know the read-write behavior of the hottest block. To do this, we define the write-to-read ratio. This ratio, when the ratio is closer to 1, the more write-dominant the traffic is. So in the figure, we plot the CDF of the write-to-read ratio under different block size. So we can see that the 94% of the hottest blocks are write dominant, so which means that the write cache at the block server can hardly work. The final question is, which cache algorithm best fits this hotspots pattern? So we run a cache simulation using the collected trace. So we select a traditional algorithm like FIFO and LRU. And we also select an emerging algorithm in this field called frozen cache FC. The frozen cache pins cache pages to the fixed LBAs and does not perform any page eviction. This can eliminate the CPU overhead of maintaining the cache line metadata and the eviction logic. We evaluate the hit ratio of these three cache algorithms under different cache sizes. So with smaller cache size, we find that the frozen cache FC performs poorly compared to the traditional ones. But as the cache size increases up to 2 GB, FD performance becomes comparable to LRU and FIFO. So we conclude that FC can achieve efficient caching at the expense of large cache size. Finally, here is the fast smart summary of our work. So this is the first field study conducted on a large-scale production EBS system. And we have highlighted new challenges and opportunities in dealing with the skewed traffic EBS. We focus on the load balancing and the traffic throttle inside the hypervisor, as well as the caching across the EBS pipeline. So, and you can find more detailed analysis and discussions in our paper. And thanks for the attention. I'm happy to take any questions.